Okay, let's unpack this. The mission today is an essential deep dive into the foundational architecture of the modern internet. We're focusing on what are called data-intensive systems. These are the applications where the real challenge isn't pure computational speed. It's about wrangling just massive data volume, all the complexity, and the relentless rate of change.
That's the critical distinction, really. If you're
Yeah.
designing anything used by millions or even just thousands of people today, you're not building a CPU-intensive application. You're building a data system. Your success, it hinges on reliably storing, managing, transforming, and retrieving data at scale.
And what's fascinating here is how these systems, which on the surface seem so different, are actually built from a common stack of conceptual building blocks. I mean, we talk about databases, caches, search indexes, message queues, batch processors, and we usually treat them as totally separate tools.
But if you connect this to the bigger picture, they are all fundamentally data systems.
Hmm.
They all face the same core problems, whether it's a traditional SQL database or, a high-throughput message queue like Kafka.
Mhm.
They all have to store data, they have to handle specific access patterns, and they need to provide guarantees about performance and durability. Understanding the mechanics beneath those interfaces is, I think, what turns a developer into an architect.
So our deep dive today focuses entirely on that foundational common ground, the concepts that apply to all data systems, whether they run on a single machine or are spread across a global cloud. We're covering four major pillars that structure this understanding. First, the core goals: reliability, scalability, and maintainability.
Hmm.
Second, the developer interface: data models and query languages.
Right.
Third, the internal physics: how we actually do storage and retrieval on disk. And finally, the reality of change: data encoding and evolution.
This dive is really about gaining fluency in the trade-offs. Every single choice in a data system is a trade-off. Do you prioritize read speed or write speed? Consistency or availability? Once you understand the underlying mechanics, you gain the power to choose the right tool for the specific job rather than, just reaching for the familiar one.
Let's jump right into those core goals then, starting with the reliability imperative. Reliability means the system does what it's supposed to do consistently, even when components fail.
And we have to start by clearly defining our terms here. Fault versus failure. A fault is a deviation in a component. A disk fails, a service times out, maybe a power supply goes bad. A failure is when the system, as a whole, stops providing the required service to the user.
So the goal isn't to prevent faults, because that's impossible.
Exactly. The goal is fault tolerance, or resilience designing the system so that those inevitable faults do not cascade into widespread failures.
What stands out to me is that we often default to thinking about hardware when we talk about faults, but the sources are actually much more diverse.
They are indeed. We can start with the obvious one, hardware faults. These are expected, particularly at scale. If you have a cluster of 10,000 disks, you should expect one to fail every single day. We handle these with redundancy RAID for disks, dual power supplies. But in massive scale cloud environments, the system has to tolerate the loss of entire machines, even entire data centers.
Right, which shifts the burden.
It shifts the fault tolerance burden from physical hardware systems to robust software mechanisms like automated failover and replication.
Then we hit the systemic issues, software errors. These seem far scarier because they can affect every node simultaneously.
They are scary. They're scary because they are harder to anticipate and test against. Unlike a hardware fault, which is usually isolated, a software bug like the famous 2012 leap-second bug that crashed tons of applications.
Oh, I remember that.
Right. That kind of systemic error in time handling affects everything running that code base. Mitigation requires rigorous testing, but also defensive coding practices, things like process isolation. If one component fails, it shouldn't take down the whole server, and constant self-checking of data invariants, like making sure a queue never magically loses messages.
And the third major fault source is the most difficult one to eliminate: human errors.
Oh, by far.
The sources are really explicit that configuration errors by operators are statistically the leading cause of major outages.
The numbers are staggering, often accounting for 75 to 90% of incidents, far, far outpacing hardware problems.
That statistic should be posted in every server room.
It really should. If you know people are the primary cause of faults, your mitigation strategy has to focus on minimizing the opportunity for error. This means designing excellent, simplified administrative APIs, not just user APIs, and providing fully featured, non-production sandbox environments.
But also you have to be able to see what's going on.
Critically, it means investing heavily in telemetry-clear, detailed monitoring that tells the operations team exactly what is wrong. so they can diagnose and recover quickly without making the situation worse.
And speaking of testing that system resilience, the fact that companies like Netflix deliberately induce faults just to ensure their systems work correctly is still mind-blowing.
The chaos monkey concept is just fundamental to modern cloud engineering. By randomly killing processes and services, you ensure that your fault tolerance mechanisms, your automatic failover, your data replication are constantly tested in the real environment.
You're not just hoping it works.
You eliminate the single point of failure that is human faith. If you aren't prepared for the loss of a machine at any given moment, you haven't truly designed a resilient system.
Okay, let's pivot to the scalability challenge. Scalability is the ability to cope with increased load, but you can't even start discussing it without defining what your load even is.
Precisely. Load has to be quantified using load parameters, and these are highly system-specific. For an analytics database, it might be the size of the dataset and the complexity of the queries. For a social network, it's often the read-write ratio, and crucially, the distribution of followers. And that's where the Twitter example comes in.
This is where it gets really interesting, contrasting the two fundamental approaches for building something like a user's home timeline on a service like Twitter.
Right. So if we look at approach 1, that's the read-heavy model. A post is simply written once to a global collection of tweets.
Simple enough?
Simple on the right side. But when a user loads their feed, the system has to look up all, say, 1,000 people they follow, fetch all their recent tweets, and then perform a complex, expensive merge and sort operation. The load is entirely on the read side.
Which is terrible if someone has millions of followers. That join gets exponentially slower.
It becomes impossible. So to solve that read bottleneck, the platform introduced approach 2, the write-heavy model. It's often called the mailbox model.
Okay, so how does that work?
The write-heavy model pre-calculates the timeline. When someone posts a tweet, the system immediately looks up every single follower and pushes that tweet directly into that follower's dedicated timeline cache.
Ah, so reading the timeline is then trivial. You just fetch the cached list.
It's incredibly fast.
Yeah.
But the load parameter shifts entirely to the write path. If a major celebrity posts, you might need to execute 30 million writes in under 5 seconds.
That massive write amplification, 30 million writes for one action, that's the new load parameter that breaks the second system. It just shows that no single architecture is perfect.
And that leads to the pragmatic hybrid solution. Most users benefit from the speed of approach 2, the write-heavy fan-out. But for the mega celebrities whose write fan-out would just crush the infrastructure, they revert to the original approach 1, the read-heavy merged fetch.
So the key load parameter there is the distribution of followers. That's what dictates which architecture you use for which users. It's a pragmatic mix of trade-offs. Okay, let's look at how we measure if these systems are actually performing. We can't just use an average response time. We need to look at distributions and the dreaded tail latency.
Right, you have to acknowledge that performance varies dramatically. You have context switches, network congestion, garbage collection pauses. That's why we rely on percentiles, the P50, the median. That's what the typical user sees. But the high percentiles, T95, P99, P99.9, are critical for measuring those performance outliers, the tail latencies.
So why are those outliers so incredibly important, even if they only affect, say, 1 in 1,000 requests?
Because they directly impact your business metrics, especially for your most engaged customers. Amazon famously realized that the customers experiencing the 99.9th percentile slowdowns were often their most valuable customers, the ones with the largest shopping carts or the most complex transaction histories.
Wow.
They found that a 100 millisecond slowdown could reduce sales by 1%. Ignoring the tail is ignoring the experience of your biggest spenders.
That's a fantastic business case for investing in optimizing milliseconds. And often, these tail latencies are caused by queuing issues, where a temporary bottleneck holds up all the subsequent requests.
Yes, that's head-of-line blocking, which is common. But in complex microservices architectures, you get something even worse. Tail latency amplification.
Amplification.
Imagine a single user request requires 10 internal calls to backend services, all running in parallel. For the user request to be fast, all 10 of those backend calls must be fast. If just one of those 10 hits the 99th percentile for latency, the entire end-user request is slowed down. The odds that at least one component will be slow increase dramatically with the number of parallel dependencies.
Which brings us to how we actually cope with load. We have the traditional choice: vertical scaling, or scaling up, versus horizontal scaling, which is scaling out.
And the decision is, again, often pragmatic. Stateless services, like caches or web servers, are easy to scale horizontally. You just add more machines. Stateful data systems are far more complex to distribute, leading to huge operational overhead. Historically, you just scaled up a database until it screamed.
Right, buy a bigger box.
Exactly. But now, with better distributed tools, the shift is toward horizontal scaling earlier in the process. We're moving toward systems that might be elastic, dynamically adding capacity in response to load, although for predictable data systems, manual scaling is often still preferred just because of the control it offers.
Let's close the goals discussion with maintainability. The sources argue, and I think rightly so, that the vast majority of software cost is in the long-term maintenance, not the initial development.
Absolutely.
So we have to design systems to minimize that future pain.
Maintainability really breaks down into three interconnected areas: operability, simplicity, and evolvability. Operability means making life easy for the operations team. This involves automating routine tasks, providing clear documentation, and ensuring that the system state is observable through comprehensive monitoring. If the team can't see what's happening, they can't fix it quickly.
And simplicity is about managing complexity, avoiding that big ball of mud syndrome where no one understands how the system works anymore.
That's where abstraction becomes our best friend. Abstraction removes accidental complexity, the complexity that isn't inherent to the problem you are solving.
Can you give an example?
For example, SQL is a giant abstraction. It hides incredibly complex details about storage structures, concurrency control, and index selection. It lets the application developer focus on defining the data they need, rather than solving internal database plumbing problems.
And finally, evolvability or agility at a system level, which is just the ease with which the system can be adapted to changing requirements.
And this is crucial, because requirements always change. The Twitter timeline example is a perfect illustration of a system being forced to evolve its core architecture, from read-heavy to write-heavy, to meet new scale requirements. Simple, well-abstracted systems are fundamentally easier to refactor, upgrade, and pivot when the business demands change.
Moving beyond the foundational goals, let's look at the first thing developers actually interact with, the data model. This abstraction layer profoundly shapes how we approach problem solving.
Data models matter so much because they determine the expressiveness and the performance characteristics of your application. When you choose a model, you choose a set of constraints and assumptions. The application object has to be layered on top of the database model, which in turn is layered on top of the physical storage engine.
The relational model, despite its age, is still the powerhouse. It stems from its ability to enforce consistency and manage complex relationships through normalization. But modern programming kind of hit a wall with it.
That wall is the object-relational impedance mismatch. If you're writing modern object-oriented code, your application deals with objects that often contain multi-valued attributes, lists of phone numbers, job histories, education records.
Right, nested data.
Exactly. To store that single object in a normalized SQL database, you have to shred it into multiple tables connected by foreign keys.
The LinkedIn profile example from the text shows this difficulty perfectly. If a user has 3 job positions, you need a user table, a position table, and foreign keys connecting them. To load the profile, you need a multi-way join or several round trips to the database.
And that's exactly why document databases like MongoDB gained so much prominence. They said, let's just store the user profile as a single JSON document. This offers excellent storage locality.
Meaning all the data is in one place.
Right. When you retrieve the profile, all the data, personal details, jobs, education, is pulled in one query, often from a contiguous block on disk.
So the document model is fantastic for one-to-many relationships, like the user-to-job relationship, which is basically a tree structure. But what happens when the real world inevitably introduces more complexity? The many-to-many dilemma.
That's the weak spot. As soon as you want to link that job history to a formal organization profile that might be shared by millions of users or tag other users in a post, you need a many-to-many relationship. The document model forces you to either duplicate the organization data in every user profile, which is denormalization and risks inconsistency.
Or you have to manually manage those relationships by storing IDs and doing what are essentially application-level joins. You're just moving the problem.
You're moving the complexity into your code.
Yeah.
And this debate, as the source materials show, is just history repeating itself. This goes all the way back to the 1970s.
Really? How so?
Absolutely. IBM's IMS was the hierarchical one-to-many model. It's the ancestor of the document model.
Yeah.
Then there was the Codasol network model, which allowed complex many-to-many structures, but did so using imperative access paths, physical pointers on disk.
So you had to tell it how to find the data.
Exactly. If you wanted a new query, you had to rewrite massive amounts of application code because your query specified how to traverse the physical links.
And the relational model won that war because of its genius. It separated the physical storage structure from the abstract query language. SQL is declarative.
That is the power of declarative querying. You tell the database what you want. The database's query optimizer, an incredibly complex piece of software, then decides the most efficient how, which index to use, the order of the join, whether to run it in parallel. This abstraction is key for maintainability and evolution.
Let's discuss schema philosophies and evolution. We have the traditional schema on write versus the NoSQL approach, schema on read.
Schema on write, used by relational databases, enforces a formal structure during the writing process. If a data doesn't fit the schema, the database rejects the write. It's like static type checking. It catches errors early.
And if you need to change the structure,
You usually run an alter table migration. Schema on read, typical of document stores, has an implicit schema that's only enforced by the application code reading the data. This is like dynamic typing for your database.
schema on read offers incredible flexibility for rapid iteration, right? If you change a field name, the new code can just check for the new field, and if it's missing, gracefully fall back to the old field name, avoiding a disruptive migration.
That flexibility is powerful for heterogeneous data or fast deployment cycles. However, the schema still exists. It's just been pushed out of the database and into the application code, where it might be less visible and harder to manage consistently, especially across dozens of microservices.
It seems like we're seeing a convergence, though.
We are. Relational databases are supporting JSON types, and document databases are adding stricter validation and declarative features. The middle ground is proving to be very powerful.
Okay, finally, let's talk about graph-like data models. When is a graph the right tool for the job?
When complex, interconnected, many-to-many relationships are the fundamental basis of your problem. Think calculating the shortest path in a road network, processing supply chain dependencies, or finding 6 degrees of separation in a social graph. Graphs are uniquely powerful because they unify different entity types, people, locations, events, into a single structure of vertices and edges.
And the most common structure is the property graph, used by databases like Neo4j.
In the property graph model, both vertices or nodes and edges, the relationships, can store key value properties, and crucially, edges have directional labels, defining the type of relationship, which makes traversal highly specific.
Could you just represent this in a relational database?
You could represent this structure using 2 relational tables, one for nodes and one for edges, but the complexity lies entirely in the query.
Right, and that's where something like Cypher, the declarative graph language, excels.
Cypher provides a concise syntax for pattern matching and traversal. You can define complex rules, like finding all people who work at a company that is located in a certain region, and you can easily specify variable length paths.
So, finding a connection 2, 3, or 5 hops away.
Exactly. And if we connect this back to the declarative versus imperative debate, trying to execute a variable length path, query like find all ancestors of a record, in standard SQL requires extremely complex and often verbose with recursive common table expressions.
It just highlights the trade-off beautifully. SQL is a general-purpose language that can do graph queries, but it's optimized for set operations. Graph query languages are optimized for traversal. Picking the right model gives you the right abstraction for the problem, which simplifies the application code massively. Let's pull the curtain back. We've covered the goals and the developer abstraction. Now we look at the internal mechanics. Chapter 3, Storage and Retrieval. How do we actually store data so we can get it back efficiently?
The process starts simply. Sequential writes are fast. If we model the world's most basic database, it's just an append-only log file. Every write is a fast sequential operation, adding data to the end of the file.
But the read operation, db_a_jet, would mean scanning the entire file from start to finish. If your file is 100 gigabytes, your lookups will be miserably slow. This immediately introduces the necessity of the index.
An index is a derivative data structure that speeds up lookups. It provides pointers to where the data is actually located. And the fundamental trade-off of all storage systems is right here. Any index speeds up reads, but it must slow down writes, because every write requires updating the index structure as well.
We're focusing on 2 major families of index structures that determine the entire performance profile of a database: log-structured storage engines and B-trees. Let's start with the log-structured approach, which leads to the LSM tree.
Log-structured engines, like those used in Cassandra, Prioritize high-rate throughput by ensuring all disk I/O remains sequential. The simplest version is the bitcask engine, an append-only log on disk, coupled with an in-memory hash map that stores the key and the byte offset of the most recent value in the log file.
So lookups are fast. It's just a hash lookup in memory and then one jump on the disk.
Mostly. But the log just keeps growing. You have to reclaim space, which requires compaction.
Okay, what's that?
Compaction breaks the massive log into smaller segments, merges those segments, discards old versions of the data, and writes the clean result back to a new file. The crucial innovation that transforms this simple log into the LSM-Tree structure is the sorted string table, or SS table. This requires that the log segments be sorted by key.
Why is that sorting requirement so transformative?
Two massive advantages. First, efficient merging. Merging two sorted lists of keys is simple and fast, requiring just a sequential pass through both files, a merge-sort algorithm. This works beautifully even if the files are larger than memory.
And the second advantage?
Efficient lookups. Because the data is sorted, you only need a sparse in-memory index. If you store the starting key for every megabyte of data on disk, finding any specific key just requires searching that sparse index and then reading and scanning only that 1 megabyte block on disk.
So the overall LSM tree flow involves writes first going to an in-memory structure, the mem table, which is fast. When that fills up, it's flushed to disk as a new sorted SS table, and the entire time, background processes are merging those older SS tables.
And this system turns random write input into efficient sequential I/O on disk, which is why it achieves extremely high write throughput. It also often uses Bloom filters, which are probabilistic data structures, to quickly tell the system if a key definitely does not exist on disk, avoiding unnecessary I/O during read operations.
Now let's contrast this with the other great index, B-trees, the decades-long standard index structure used by most traditional relational databases.
B-trees take a page-oriented approach. They break the database into fixed-size blocks, typically 4 KB, and are designed to perform updates in place. Data is sorted, but if you update a record, you actually overwrite the page where that data lives. This structure is highly optimized for the physical reality of magnetic disks, minimizing the necessary seek operations.
But in-place updates sound dangerous. If the system crashes mid-update, you could corrupt the entire index structure.
That's the major engineering hurdle B-trees solve with the write-ahead log, or WAL. Before any modification is made to the actual B-tree page on disk, the intention to modify must first be appended sequentially to the WAL.
Ah, so it's a journal.
It's a journal. If the system crashes, the database uses the WAL to restore the B-tree to a consistent state.
Okay, so comparing the two, the LSM tree is optimized for sequential writes, and the B tree is optimized for predictable random access reads. What are the key trade-offs?
The trade-offs center on predictability and endurance. LSM-Trees sustain higher write throughput, but they suffer from write amplification.
Meaning the same piece of data gets written over and over.
Exactly. Data gets systematically rewritten multiple times during compaction, which can be a concern for the lifespan and performance of SSDs. Furthermore, LSM-Tree read performance can suffer from high tail latencies because those background compaction processes can interfere unpredictably with concurrent read and write operations.
Whereas B-trees offer highly predictable read performance. For any given key, the data exists in exactly one place, and the path to that data is known and stable.
And that single location guarantee also makes B-trees the index of choice for systems requiring strong transactional semantics and strict locking. It simplifies the management of concurrent operations significantly compared to multi-version log-structured indexes.
Before we leave storage, we have to talk about the great divergence in database usage. Transaction processing versus analytics. These are fundamentally different workloads.
Completely different. They require completely different architectural approaches. Online transaction processing, or OLTP, is the operational workload. High volume, low latency reads and writes on small numbers of records focused on the current state of data-like processing and order on a website.
And the other side.
Online Analytical Processing, or OLAP. This is the business intelligence workload. Complex queries that aggregate over vast numbers of historical records to find trends and patterns.
And the solution to managing these conflicting needs is the data warehouse, using an ETL process.
Correct. You separate the workloads. Data is extracted from the operational OLTP database, transformed into a schema optimized for analytics, often the star schema, and then loaded into a separate data warehouse. This ETL process protects the mission-critical OLTP system from slow, complex analytical queries that would otherwise just monopolize all the resources.
A key technology optimized specifically for this OLAP workload is column-oriented storage.
This is a brilliant structural shift. Traditional row-oriented storage loads an entire record, an entire row, even if your query only needs 2 or 3 columns out of 100. Column-oriented storage flips this. It stores all the values from each column together.
So if a query is analyzing sales figures by date, it only needs to read the date column and the sales column. It just ignores everything else, minimizing disk I/O dramatically.
And that separation enables 2 huge performance wins. First, compression. Columnar data compresses extremely well because there's often high redundancy within a spindle column, like the same product ID repeated millions of times.
And the second win?
Vectorized processing. The database can perform simple, tight CPU loops on chunks of compressed data directly, processing rows way faster than traditional models, achieving performance gains far beyond just reducing disk access.
But wait, if everything is sorted and compressed like that, doesn't writing new data become incredibly difficult?
It does. Updates require rewriting entire column files, which is costly. However, modern column stores borrow principles from LSM-Trees.
Ah, so new writes go to a buffer.
Exactly. New writes are directed to a fast in-memory buffer, the equivalent of a mem table, and those writes are merged into the main columnar files in a bulk process in the background. This allows column stores to maintain high write throughput while preserving their analytical read efficiency.
Let's move to the last critical pillar, data encoding and evolution. The hard truth of software engineering is that data outlives code. This means old code, old data, and new data must all coexist gracefully.
The central requirement here is robust compatibility. You need backward compatibility. Newer code has to be able to read data written by older code, and often more challenging, forward compatibility. Older code has to be able to read and gracefully ignore data written by newer code.
If you can't do that, rolling upgrades become a nightmare.
Impossible.
We started with the human-readable formats, JSON and XML, but they are surprisingly problematic for rigorous data interchange.
They're verbose, for one, and they suffer from ambiguity. JSON, for instance, doesn't distinguish between large integers and floating point numbers. If your ID numbers exceed 2 to the power of 53, standard JavaScript clients will lose precision.
So people end up encoding them as strings, which is a hack.
It's a hack. And compatibility relies entirely on developers manually agreeing to ignore unknown fields.
So you contrast that with the binary schema-driven formats. Apache Thrift and Google Protocol buffers, they solve the size and precision issues instantly.
They're far more compact and efficient because they rely on an explicit, machine-readable schema. The key mechanism for compatibility is the numeric field tag. Instead of writing out the verbose field name, the data is encoded with a small integer tag, like username 1.
And new code can just add fields with new tags.
Right. And old code, when it encounters a field tag it doesn't recognize, simply skips it. That guarantees forward compatibility. You just have to follow one rule. Never change or reuse a field tag number.
Now, here's where it gets really interesting. Avro's schema resolution model. It handles compatibility in a fundamentally different way than protobuf or Thrift.
Avro requires that both the writer's schema, how the data was written, and the reader's schema, how the code expects to read it, be available during the read process. The Avro library acts as a mediator. It looks at both schemas and translates automatically.
So if the writer wrote the data with a field called name and the reader expects first name and last name,
Avro can handle that transformation automatically, provided the schemas define the mapping or the necessary default values.
that seems much more powerful for data migration and evolution, especially since it automates providing default values if a field is missing in the data.
It is, especially for use cases where schemas are dynamically generated. If you're using Avro to dump a relational database, Avro can generate the schema based on the column names. If you use protobuf or Thrift, you'd have to manually assign and manage numeric tags for hundreds of columns, which becomes a real operational headache. Avro's schema-driven approach is uniquely suited for evolving complex datasets.
Let's quickly review the 3 primary ways data flows through a modern distributed system and how crucial compatibility is in each mode.
Okay, first, you have data flow through databases. The writer is the application, and the reader is also the application, but possibly running a different version 6 months later. We need both backward and forward compatibility, and a massive practical risk here is the read-modify-write cycle.
Explain that.
If old code reads a record written by new code, and the old code doesn't know about the new fields, it might inadvertently drop or ignore those new fields when it writes the record back to the database. You get data loss.
That's bad. Okay, second data flow mode. Data flow through services, so REST and RPC, which enable microservices architectures.
The historical failure here was the older remote procedure call, or RPC model. It
Mhm.
tried to achieve location transparency, making a remote network call look exactly like a local function call.
Which is a lie.
It's a fundamentally flawed abstraction because networks are unreliable.
Yeah.
Network calls suffer from variable latency, timeouts, and partial failures, which local calls just do not.
And the modern solution, like REST and modern gRPC, acknowledges that network reality.
Precisely. REST embraces simplicity, using standard HTTP features and JSON. Modern RPC frameworks are optimized for efficiency, but acknowledge the network reality by using concepts like futures and streams. Compatibility here is required for both the request, which needs to be backward compatible from the client's perspective, and the response, which needs to be forward compatible.
And finally, message passing data flow using message brokers or queues.
This is a vital mechanism for decoupling services. A service publishes a message, and another service consumes it asynchronously. The broker acts as a buffer against overload, which is excellent for system stability. However, the publisher and consumer are often deployed and versioned completely independently, possibly by different teams. If the encoding schemas are not robustly compatible, you risk data parsing failures downstream, causing catastrophic cascading failures across independent services.
So what does this all mean? We've completed a massive exploration, moving from the high-level goals of resilience and scale down through the conceptual data models and right into the physical layer of storage and encoding. The takeaway for me is clear. The choices you make at every single layer, from deciding on a document versus a relational model to picking an LSM tree versus a B tree, create systemic trade-offs that define the limits and capabilities of your application.
To recap the most essential takeaways, reliability is achieved through robust tolerance of hardware, software, and most importantly, human faults. Scalability demands that you quantify your load with specificity like follow or fan-out, and that you manage the business risk of high percentile latency. And data models must align with your relationship structure. Forcing complex relationships into a poor-fitting model just shifts all that complexity into your application code.
And storage performance is determined by your dominant workload. OLTP favors B trees for predictable random access, while OLAP demands columnar storage optimized for sequential scans, deep compression, and vectorized processing.
Finally, evolvability is not an accident. It is engineered using robust, schema-driven encoding formats like protocol buffers and Avro. Those formats guarantee the backward and forward compatibility necessary for safe, rolling deployments in a dynamic system.
If we connect this to the bigger picture, we're seeing this incredible convergence across the entire data landscape. Relational databases support JSON. Document stores are adding declarative querying and transactional features.
And storage engines are borrowing from each other. LSM-Tree compaction ideas are showing up in column stores, B-tree stability techniques in log-structured formats. The lines are blurring.
It raises an important question for you to mull over. Given that every successful data system is now a pragmatic hybrid of these approaches, does the future lie in a single, truly polymorphic database?
A system that can dynamically adapt its internal storage structure and indexing strategy to optimize itself for the specific workload being thrown at it at any given moment, whether that's high-throughput transactions or massive analytical queries. The boundaries are blurring, and that convergence is where the next generation of architectural innovation will happen.
Thank you for joining us for this deep dive into the foundations of data systems. We hope this knowledge helps you transition from application developer to confident data system designer.